Welcome to the Science of Everything channel. Tonight, let us cast our gaze beyond the radiant band of the Milky Way and into the depths of space, toward a silent giant, the Andromeda Galaxy. On a moonless, clear night, it appears merely as a faint, fuzzy patch suspended in the constellation of Andromeda, gentle and unassuming. But do not be deceived by this modest facade. This patch of light is a cosmic island composed of over 1 trillion suns, its elegant spiral arms stretching across hundreds of thousands of light-years through the void. Every glimmer of light that reaches our eyes tonight began its journey 2.5 million years ago, long before our ancestors took their first tentative steps across the African savanna. This light carries countless stories: the fiery life of a star, the nebulous past of a gas cloud, or the silent epic of a world we will never reach. Within its vast arms, the birth and death of stars never cease, enacting an eternal drama of creation and annihilation. Andromeda is far more than a simple point of light. It is our nearest grand neighbor, currently striding steadily toward us through the deep darkness, drawn by the invisible tug of gravity. Billions of years from now, a momentous encounter across cosmic time is fated to occur, as it merges with our own Milky Way to give birth to an entirely new celestial body. If you enjoy these quiet contemplations under the stars, consider liking this video or leaving a comment with your thoughts. Every interaction acts like a tiny beacon in the dark, guiding other friends seeking cosmic solace to this corner of the universe. For now, relax, slow your breathing, and let your thoughts grow light. Allow the infinite cosmos to carry your curiosity as we embark on this journey together. The Andromeda Galaxy is the nearest heavyweight to our Milky Way. Among the countless twinkling galaxies in the universe, it is the closest large spiral galaxy, lying approximately 2.5 million light-years away. On a cosmic scale where distances are routinely measured in hundreds of millions of light-years, this is practically next door, like looking across the street. Yet even this short distance is unimaginably vast. Even traveling at the speed of light, one would need 2.5 million years to make the trip. It is precisely this privileged proximity that provides astronomers with a perfect laboratory, allowing them to scrutinize the structure of a galaxy similar to our own from the outside, thereby understanding how stars, gas, and dust are born, move, and evolve within spiral arms. Through powerful telescopes, Andromeda's intricate structure gradually comes into focus. Its glowing disk spans the sky, while dark dust lanes flow like black streams through rivers of starlight rushing toward the galactic core. Each high-resolution image offers us a glimpse of a familiar cosmic order, albeit on a scale so grand it takes our breath away. Andromeda is like a towering cosmic mirror, reflecting what our own galactic home might look like to a distant alien observer. Because of this, it has become one of the most thoroughly observed objects in modern astronomy, a living textbook for studying how galaxies grow, interact, and evolve over time. In its ancient light, we see not only the face of our neighbor but also read the fate of our own galaxy written in the distant future. Within Andromeda's massive spiral arms, astronomers estimate there are over 1 trillion stars. Each burns with its own unique temperature, color, and rhythm of life. These stars fill every corner of the galaxy, from the densely packed central bulge, composed mostly of ancient stars, to the broad, winding arms that eventually fade into the profound darkness. Among them are massive, brilliant blue giants, whose lives are intense and brief, ending in spectacular supernova explosions that scatter forged heavy elements into the surrounding space. There are also multitudes of dim, mild-mannered red dwarfs, capable of burning stably for trillions of years, their lifespans bordering on the eternal. It is the collective light of this immense stellar population that possesses the energy to traverse 2.5 million light-years of emptiness, allowing us to see it. This incalculable number of stars grants Andromeda its gravitational dominion and structural majesty. And if even a tiny fraction of these stars host planets, the number of potential worlds in this galaxy would exceed imagination. perhaps outnumbering all the grains of sand on all the beaches on Earth. Amazingly, you can see it with the naked eye. On a clear, moonless night, far from city lights, if you look toward the constellation Andromeda with enough patience, that hazy, elliptical glow will appear. It emits a soft, uniform radiance. This is no optical illusion. It is the distant whisper of over 1 trillion stars merging their light. To ancient stargazers, it was an eternal mystery, a ghostly mist neither star nor planet, hanging silently at the edge of perception. It was only when telescopes were turned upon it that humanity glimpsed its true nature. It was not a nebula at all, but a complete universe of stars beyond our own galaxy. When you spot it with your naked eye, you are receiving light that set out on its journey millions of years before human civilization even existed. You are crossing time and space to share the same cosmic instant with countless ancestors who gazed upon that same light throughout history. For a long time, it was mistaken for a nebula within our own galaxy. For centuries, even the earliest telescopic astronomers thought Andromeda was a luminous cloud of gas and dust inside the Milky Way. In the 17th and 18th centuries, it was catalogued as the Andromeda Nebula, one of many such fuzzy objects. This notion persisted until the 1920s, when Edwin Hubble used the powerful 100-inch telescope at Mount Wilson Observatory to examine it more deeply. Within that hazy fog, he discovered a special type of star, Cepheid variables. These stars act as standard candles in the universe. Their regular pulsation periods directly reveal their true brightness. By comparing their intrinsic luminosity to how dim they appeared from Earth, Hubble calculated that Andromeda lay far beyond the boundaries of the Milky Way. This discovery was revolutionary. It proved that the universe was vastly larger than humanity had imagined, filled with countless island universes just like our own. From that moment on, the Andromeda Nebula was correctly recognized as the Andromeda Galaxy, forever changing humanity's understanding of cosmic scale. Therefore, what we see right now is not Andromeda as it is today, but as it was 2.5 million years ago. Every photon hitting your pupil began its long trek when humans were still primitive beings on Earth. That light traversed the cold, lonely abyss between galaxies, carrying records of ancient stars from lifetimes ago. Some of those stars may have already burned out, exploded violently, or faded into white dwarfs or neutron stars. Yet their light continues its journey, undeterred. Observing Andromeda is itself a form of time travel. The light entering our telescopes tonight departed during an age when human ancestors were still chipping stones and staring into campfires. Thus, every gaze at Andromeda is both a scientific observation and a quiet connection to the remote past. Its glow is a message from antiquity, traversing time without alteration. Though it appears static, Andromeda is racing toward us at a staggering speed of over 300 kilometers per second. Astronomers discovered this hidden motion by analyzing the spectra of its stars. The frequency of its light is slightly shifted toward the blue end, a phenomenon known as blue shift, definitive evidence that the light source is approaching the observer. Amidst a universe that is generally expanding, with most galaxies moving away from us, Andromeda is a rare exception charging straight for us. This is the result of powerful mutual gravitational attraction between two giant systems. This approach is slow yet inexorable, unfolding over billions of years. It is imperceptible to the naked eye, but unstoppable. In this quiet advance, we see both the destined future of the Milky Way and witness the slow, grand choreography of gravity upon the canvas of the cosmos. Using space observatories like the Hubble Space Telescope and the Gaia satellite, scientists have mapped Andromeda's trajectory with extreme precision. The data shows it is not going to simply pass us by. It is locked on a collision course. Computer simulations project this trajectory into the future, revealing how gravity will stretch and twist the spiral arms of both galaxies into glowing tidal streams before they slowly spiral into a merger. The first close encounter will occur in about 4 billion years, followed by a prolonged fusion process that may last for billions more. During this time, the night sky above any surviving Earth will be completely transformed, dominated by massive arcs of stars forming a new Milky Way. Mapping this collision course allows humanity to peek into the distant future inscribed in the laws of physics, a calm and certain destiny. The ultimate meeting of the Milky Way and Andromeda will not be a catastrophic explosion, but a slow, graceful cosmic dance lasting billions of years. Their spiral arms will twist and intertwine under gravitational influence, forming long rivers of stars. Since the spaces between stars are so vast, direct collisions between individual stars will be exceedingly rare. However, their orbital paths will be completely rewritten, weaving new patterns within the combined gravitational field. Over time, the two galaxies will merge into a single, massive elliptical galaxy, featuring a bright, dense core and broad, diffuse outer regions. To any surviving inhabitants on a planet, the sky will be filled with the intertwined, brilliant glow of stars from both original galaxies. This merger will mark the next chapter in our corner of the universe, as two great spirals become one persistent, shining whole. Astronomers have already named this future newborn Milkomeda, a portmanteau blending the names Milky Way and Andromeda. This new galaxy will likely contain trillions of stars, spanning hundreds of thousands of light years. At its heart, the supermassive black holes of both galaxies will circle each other, eventually merging in a colossal release of energy. Milkomeda will shine as a smooth, elliptical galaxy. To any distant observer, it will appear serene and symmetrical, an elegant monument to the gravity and time that shaped it. Sealed within its light will be the complete history of two galaxies that once gazed at each other across the darkness. It reminds us that even in the absolute silence of space, everything is in motion and eternity is not the norm. Andromeda is one of the largest spiral galaxies ever measured by humanity. Its disk diameter exceeds 220,000 light-years, nearly twice that of the Milky Way. Its defining, beautifully majestic spiral arms wind outward from a bright central bulge, consisting of vast bands of stars, gas, and interstellar dust. These arms are not fixed, solid structures. They are density waves propagating through the galactic disk, much like ripples spreading across a pond. When the wave front passes through a gas-rich region, it compresses matter, triggering bursts of star formation that instantly light up the arms with young, blue star clusters. Between the arms lie dark dust lanes, absorbing and scattering light, adding layers of depth to the structure. Studying these arms through telescopes reveals how matter flows, collapses, and renews itself on grand timescales. The delicate balance between order and chaos within the arms tells the story of how galaxies maintain their vitality and constantly reshape themselves within the bonds of gravity. In terms of both size and mass, Andromeda vastly outweighs our Milky Way. Its enormous disk spans over 220,000 light-years and contains an estimated trillion stars, compared to the Milky Way's 200 to 400 billion. If the human eye could fully perceive the extent of Andromeda's light, it would appear several times wider than the full moon in the night sky. Its immense scale reminds us that galaxies are not uniform pinwheels of light, but sprawling cosmic metropolises composed of countless suns, nebulae, and invisible matter. Compared to Andromeda, the Milky Way is like a smaller sibling orbiting nearby, bound by gravity and destined to become one. The core of Andromeda radiates a golden glow from tens of billions of ancient stars. This central region is bright and dense, far outshining most areas of its disk. Its light is soft, tending toward gold, the cumulative color of countless stars that have been burning for over 10 billion years. Most are older than the Sun, smaller and more stable, slowly consuming their final fuel. These ancient stars are packed so tightly that in some regions, they may be separated by only a few tenths of a light-year. From that crowded core, light still travels over 2 million years to reach us. The golden hue of the core tells astronomers that this is a neighborhood of old stars, The frenzied era of violent star birth ended long ago. In a sense, Andromeda's core is a living fossil, preserving its earliest relics, glowing silently through the ages. Deep within the radiant core of Andromeda, astronomers have detected stars orbiting an invisible object at incredible speeds. The only logical explanation is that a supermassive black hole, weighing millions of times the mass of the Sun, lurks there. Its gravity is so powerful that not even light can escape from within its boundary. Around it, stars perform a gravitational ballet that has lasted for 10 billion years. The space near the black hole is likely filled with a swirling accretion disk of hot gas and dust, emitting blinding radiation before the matter plunges into the abyss. Though the black hole itself is invisible, its presence is confirmed by the frantic motions of nearby stars and the radiation emitted by the superheated matter it ensnares. It is the silent engine shaping Andromeda's core architecture and dictating the rhythm of everything within its gravitational reach. Even more intriguing, when astronomers examine the exact center of Andromeda at extremely high resolution, they found something unusual. The light did not seem to emanate from a single point, but rather from a pair. This sparked a bold hypothesis. Andromeda's core may not house one, but two supermassive black holes, locked in a slow, dancing orbit around each other. Such a pair would likely be the orphaned remnant of a past galactic merger, where the cores of two colliding galaxies became gravitationally bound, beginning a long, slow spiral inward. On cosmic timescales, they will draw closer and closer, releasing gravitational waves that ripple spacetime, eventually merging into one. If this theory proves true, then this hidden duo at Andromeda's heart offers us a preview of our own galaxy's future, for the Milky Way also harbors a central black hole, which may one day meet Andromeda's heart in a similar cosmic embrace. Surrounding Andromeda's bright spiral disk is a vast, diffuse halo extending far beyond the visible portion. This halo consists primarily of thin hot gas, interstellar dust, and the dominant component, dark matter. It stretches over 1 million light-years from the galactic center, several times the radius of the visible disk. Floating within this giant cosmic atmosphere are ancient globular clusters and streams of stars stripped from devoured galaxies. Scientists study it using ultraviolet and X-ray observations, tracking the faint signals of atoms excited by distant starlight. Though ethereal, this halo is crucial for maintaining Andromeda's structure. It serves as a reservoir of matter and defines the boundaries of its gravitational influence. It is the galaxy's ghostly aura, invisible yet immensely powerful, blending seamlessly into intergalactic space. A startling fact is that despite the 2.5 million light-years of void separating the Milky Way and Andromeda, recent observations suggest that the outer edges of these diffuse halos may already be touching. This implies that long before the visible parts of the galaxies collide, their invisible atmospheres have already begun to interpenetrate and mingle, exchanging energy and particles in the void. This idea reshapes our understanding of cosmic borders. Boundaries in space are rarely sharp and solid. Galaxies have been whispering of their proximity for eons, interacting through their faint, extended presences long before the dramatic collision begins. Detailed astronomical mapping has also revealed that Andromeda's disk is not a perfectly flat plane, but is warped, like a slightly bent record. Certain sections are lifted or depressed by thousands of light-years. Such large-scale warping is typically a scar left by gravitational interactions with other galaxies. This pattern suggests that beneath Andromeda's serene, elegant arms lies a more turbulent history. Even across cosmic distances, we can still see the lingering ripples of those ancient interactions, frozen in the distribution of stars. It is a silent declaration. No galaxy, however peaceful it may appear, can remain absolutely still amidst the ceaseless tides of the universe. Astronomers speculate that this warp likely stems from past galactic collisions. Galactic encounters don't happen with fire and thunder. Direct star collisions are highly improbable, but their collective gravity acts like invisible hands, slowly and thoroughly reshaping the galaxy's forms. For Andromeda, its warped disk and faint stellar streams in the periphery are likely enduring imprints of close encounters with smaller galaxies in the distant past. Those unfortunate passers-by were torn apart and consumed by Andromeda's powerful gravity. Their remnants were absorbed, and the distribution of stars was perturbed, like ripples frozen on a pond after a stone is thrown. By studying these warp patterns, scientists can reconstruct Andromeda's merger history, tracing the ghostly fingerprints of galaxies that vanished long before life appeared on Earth. Like the Milky Way, Andromeda is not alone. It is surrounded by dozens of smaller satellite galaxies. These companion galaxies vary in size. Some are bright and distinct, others are mere faint smudges barely detectable by telescopes. Most are dwarf galaxies rich in ancient stars, their orbits dictated by Andromeda's immense gravity, slowly being pulled closer over time. The existence of these companions reveals to astronomers how large galaxies grow. Through countless such gravitational interactions and gradual mergers, Andromeda has incorporated them into its family. Therefore, the sky around it is far from empty. It is filled with quiet motion, teeming with small galaxies orbiting the giant neighbor. Many of these companion galaxies are currently being slowly consumed by Andromeda. Under the pull of strong gravity, the gas and stars of the smaller galaxies are stretched and stripped away, forming long tidal streams that spiral into Andromeda's main body like cosmic ribbons. This galactic cannibalism is slow and silent, yet it is one of the most common stories in the universe. Through this process, galaxies grow larger, assimilating the matter of their neighbors. Observations have already revealed these faint arcs and streaks around Andromeda. Each is the spectral wreckage of a devoured companion galaxy. The light of these streams tells a tale of creation through destruction, small galaxies sacrificing themselves to build a larger, more complex whole. Even now, somewhere in Andromeda's vast halo, new streams may be forming. Interestingly, not all stars that belong to Andromeda today were born there. Many are immigrant stars, born in smaller galaxies that later merged with Andromeda, or drifters captured by its gravity during a close pass. As these smaller systems disintegrated, their stars were flung into new orbits within Andromeda's halo and disk. Astronomers can identify them by analyzing their chemical composition, as the abundance of elements carries a unique signature of their original homes. Some stars have extremely low levels of heavy elements, marking them as ancient visitors from primordial galaxies in the early universe. Together, they reveal that Andromeda's growth was a collective process, shaped by multiple merger events. Each new addition brought its own history and light, eventually weaving into a magnificent galactic tapestry, telling the story of diverse origins unified across time and space. The remnants of devoured galaxies trail stellar streams stretching hundreds of thousands of light years. Andromeda's outer regions are interwoven with these slender, faint trails of starlight, the debris of smaller galaxies torn apart and absorbed by gravity. Some streams precisely trace the paths those lost galaxies once followed. By studying their shapes and motions, astronomers can reconstruct the timeline of Andromeda's multiple mergers. Each stream is a fossil record of an ancient event. These streams also help reveal the distribution of dark matter, as their paths bend according to the unseen gravitational landscapes surrounding Andromeda. Though faint, they are among the most moving features of a galaxy, glowing softly in the dark, serving as silent witnesses to billions of years of cosmic history. The deeper we study Andromeda, the more evidence we find suggesting it is a giant built through countless acts of cosmic consumption. Its halo contains stars of multiple origins. Its disk exhibits warps and ripples. Its outer regions sparkle with debris from cannibalized galaxies. Every sign points to a long evolution shaped by repeated mergers. Astronomers no longer view Andromeda as a single entity, but as the accumulated sum of dozens of smaller galaxies. Even its elegant spiral arms may have been reshaped by these encounters. This form of galactic cannibalism, while not violent, is part of the slow metabolism of the universe. Galaxies grow by absorbing others, recycling their stars and gas, forging new generations of light. Thus, Andromeda's grandeur is also a story of transformation over time. However, the visible stars and gas account for only a small fraction of Andromeda's total mass. The vast majority is made up of mysterious stuff that neither emits, absorbs, nor reflects light, what astronomers call dark matter. Its existence is revealed solely through its powerful gravitational effects. This invisible force holds the galaxy together and dictates the ultra-fast motion of its stars. Without dark matter, the stars at Andromeda's outskirts would have long since flown away. Dark matter is likely composed of exotic particles that interact only via gravity. It envelopes Andromeda like a massive, transparent cocoon, with a mass perhaps 10 times greater than all the visible matter. It forms an enormous dark halo extending far beyond the visible disk, influencing the rotation of the entire galaxy. Although it cannot be directly detected, its influence is everywhere. In this sense, Andromeda is not just a collection of stars, but a massive gravitational enigma. Its luminous disk floats in an ocean of invisible matter, persistently reminding us that the vast majority of the universe remains hidden from our view. The motion of its stars clearly reveals the presence of this invisible mass. When astronomers measured the orbital speeds of stars at different locations in Andromeda, they discovered a startling fact. Even in the outer regions, far from the center where visible matter drops off sharply, the stars were still moving incredibly fast. This implies that some additional, invisible source of gravity must be present to hold these high-speed stars captive within the galaxy. This hidden source is dark matter. By charting the rotation curve from the core to the edge, scientists can map the distribution of this invisible matter throughout the galaxy. The smooth, consistent motion of Andromeda's stars outlines a massive dark halo tightly wrapped around it, extending far beyond the visible boundary. Thus, Andromeda stands as one of the best cosmic laboratories for understanding how dark matter shapes the magnificent structures of galaxies. Scattered along Andromeda's spiral arms are vast nebulae composed of glowing hydrogen gas, stretching thousands of light-years and glowing pinkish red. These giant clouds are the raw material for birthing new stars. When the ultraviolet radiation from young, hot stars within them excites the surrounding hydrogen, it produces this dreamy color. These glowing regions are active stellar nurseries, where gravity gathers dense clumps of gas until temperature and pressure ignite nuclear fusion, and a new star is born. Observing these hydrogen clouds allows astronomers to witness Andromeda's ongoing life cycle. Even in such an ancient, expansive galaxy, the process of creation never ceases. The light from these nebulae also began its journey over 2 million years ago, offering us a glimpse of Andromeda's present in the distant past. The beauty of these glowing nebulae reminds us that even in the deep silence of space, new light is always being born quietly. Inside these massive hydrogen clouds, tiny clumps of gas collapse under their own gravity. As density, pressure, and temperature surge, the fire of nuclear fusion ignites, and a star is born. These stellar cradles are turbulent yet delicately fragile, intertwining glowing gas with dark dust lanes that drift like smoke. Many newborn stars appear in clusters, illuminating their surroundings with their brilliant light. Some are massive, short-lived stars destined to end in supernovae within a few million years. Others will burn stably for over 10 billion years. Observing these regions in Andromeda allows astronomers to witness the very same processes that created our own Sunday. It reminds us that the cycle of cosmic birth continues in every corner. Above and below Andromeda's spiral disk, astronomers have also detected gigantic bubbles of hot gas, tens of thousands of light-years in diameter. These colossal structures are clearly visible in the X-ray spectrum, testifying to the immense energy released in the galactic core or in regions of active star formation. They are likely formed by the shockwaves of countless supernova explosions or powerful stellar winds pushing gas outward over millions of years. These bubbles act like the galaxy's breath, expelling energy and matter into the surrounding halo. Studying them reveals how galaxies regulate their own growth, balancing creation and release. Though invisible to the naked eye, these giant bubbles mark the vibrant signs of life in Andromeda. It exhales heat and motion into the silent darkness, showing that even a galaxy pulses and changes. The formation of these giant bubbles is likely linked to occasional violent, starburst events in the galaxy's history. When certain regions of Andromeda experience a sudden, intense spike in star formation, massive numbers of young, large stars are born and die in quick succession. The combined force of their stellar winds and supernova explosions can blast hot gas violently outward, creating enormous cavities expanding above and below the galactic plane. These bubbles are footprints of Andromeda's most active moments. The process also enriches the surrounding gas with heavy elements forged in stellar interiors, providing fertilizer for future generations of stars. The presence of these bubbles indicates that a galaxy is far from a static system. It is a living ecosystem that breathes, burns, and renews itself. Meanwhile, supernova explosions continually reshape the interstellar medium within Andromeda. While most stars live long, uneventful lives, massive stars always end their lives in the spectacular collapse of a supernova. The energy released in an instant exceeds the total output of the Sun over its entire lifetime. In Andromeda's long history, such explosions have occurred countless times. Each blast sends shockwaves rippling through and fertilizing the interstellar medium, compressing nearby gas clouds and triggering new waves of star birth. Heavy elements forged in the dying star's cores, iron, gold, oxygen, are scattered into space, becoming the raw materials for future planets and even life. Through this continuous cycle of death and rebirth, Andromeda's structure and composition are constantly updated. Its luminous beauty, visible across millions of light years, is built upon this ancient rhythm of cosmic transformation. In full-color images taken by telescopes, Andromeda's spiral arms blaze with thousands of young, blue stars. These young suns are massive, hot, and intensely luminous, but short-lived, often burning out their fuel in just a few million years before perishing in supernovae. They are born in clusters within giant hydrogen clouds, and their fierce ultraviolet light excites the surrounding gas, clearly outlining the elegant contours of the spiral arms. These blue stars are markers of the galaxy's ongoing creativity, active zones where new light is still being formed. They live brilliantly, die dramatically, and illuminate the path of the galaxy's continued evolution. When we gaze at Andromeda's glowing arms, we are seeing the vigorous energy of cosmic adolescence scattered across the night sky. In stark contrast is the central region of Andromeda. It is filled with older yellow and red stars, radiating a warm, golden glow. These ancient suns have long passed their prime, burning with a softer light. They are densely packed together, collectively forming the amber-hued halo that dominates the galactic bulge. After 10 billion years, star formation in this region has nearly ceased, leaving behind a dense, stable population of elderly stars orbiting the hidden black hole in complex patterns. Studying this central cluster provides astronomers with clues about Andromeda's earliest history. The color contrast between the bright blue arms and the golden core tells a story about time itself, revealing how galaxies gradually soften as their energy wanes with age, eventually settling into a tranquil glow. Although Andromeda's spiral structure appears symmetrical, its internal star formation activity is distributed extremely unevenly. Some regions blaze with newly born star clusters, while others are relatively dark and quiescent. This variation is determined by the uneven distribution of gas, dust, and magnetic fields across the galactic disk. Where cold hydrogen gas is abundant and dense, gravity easily triggers bursts of star formation. Where gas is thin or overheated, the process stalls. Density waves generated by the spiral arm motion compress gas in a rhythmic pulse, igniting stars along narrow, curved bands like a cosmic heartbeat. Observing this pattern helps us understand how a galaxy breathes, forming stars in pulses rather than continuously. Andromeda's uneven tapestry of light reveals that even on a galactic scale, creation unfolds in complex rhythms, balancing quiet zones with energetic flares. Interestingly, star formation within Andromeda has gradually slowed in its interior, while the outer regions continue to shine brightly. In the inner galaxy, the raw material for star formation has been largely depleted, either converted into stars or blown away by past stellar winds. Consequently, the inner disk is now dominated by the steady, soft glow of older, longer-lived stars. In contrast, the outer regions of the galaxy remain rich in cold hydrogen gas, allowing new stars to continue forming far from the center. This difference creates a kind of temporal stratification within Andromeda. An ancient core coexists with a youthful edge. Studying this contrast allows astronomers to trace how a galaxy evolves from an active star-forming system to a calmer, more mature structure. Andromeda's bright outer rim reminds us that even an ancient galaxy retains corners of vitality in its outermost arms, where the cosmic cycle of birth and renewal continues quietly. When viewed through powerful telescopes, you will see that Andromeda's glowing arms are laced with intricate dark ribbons. These are interstellar dust lanes composed of tiny carbon and silicate grains ejected by dying stars. They absorb and scatter the light from stars behind them, creating the smoky patterns that coil through the glowing spirals. However, these dust lanes are not mere shadows. They are the topsoil of the galaxy. Within them exist cold, high-density regions where new stars are currently being nurtured. The complex shapes of the dust lanes trace the flow paths of gas within Andromeda's gravitational field. Observed in infrared wavelengths, these dark bands come alive, glowing faintly with thermal radiation absorbed from nearby stars. Through their exquisite patterns, we catch a glimpse of the silent choreography of cosmic creation, the very process that once created the sun, the earth, and every atom in our bodies. The view through infrared telescopes has completely changed our understanding of these dust lanes. To the naked eye or in optical telescopes, they are silhouettes against the starlight. But to infrared telescopes sensitive to heat radiation, those shadows vanish, replaced by a softly glowing tapestry of light emitted by the dust itself. Heated by starlight, the dust radiates faint warmth detectable only at longer infrared wavelengths. Using infrared observations, scientists can penetrate the dusty veil to see young stars still shrouded in their birth nebulae. What once seemed like dark, empty voids transforms into a warm, hidden landscape of activity. This reminds us that even in the coldest corners of space, every particle carries energy, and every shadow may conceal a light. Andromeda's light is not limited to the visible spectrum. It shines across the entire electromagnetic spectrum. Observed through ultraviolet telescopes, a different picture emerges. The spiral arms flare with bright, energetic spots where clusters of massive young stars reside. These newborn stars emit intense ultraviolet radiation, heating and sculpting the surrounding gas. By mapping this UV glow, scientists can track the galaxy's most active star-forming regions and measure its rate of creating new stars. Andromeda's ultraviolet image looks almost like a skeletal framework, revealing the scaffolding of its inner stellar nurseries, like glowing embers within the spirals. Seeing Andromeda in UV light is akin to watching it live and breathe in real time. In the radio waveband, Andromeda presents yet another face. Radio telescopes detect the faint signals emitted by massive clouds of cold hydrogen gas within the galaxy. This gas is the reservoir for future stars, not yet ignited. By tuning into the characteristic frequency of neutral hydrogen, scientists can map the distribution of this cold gas in Andromeda, revealing that its massive spiral structure extends even beyond the visible disk. Thus, Andromeda's radio image is like a blueprint for its future, a silent, invisible foundation supporting the brilliant stars that will one day light up its arms again. From radio waves to gamma rays, Andromeda tells a different chapter of its story at every wavelength. Radio waves reveal its cold gas and vast structure. Infrared shows the warmth of dust and nascent stars. Visible light outlines the grand spiral itself. Ultraviolet marks the high-energy, youthful regions, and X-rays expose the violent activity of exploded stellar remnants. All these layers combine to form a complete portrait of a vibrant, complex galaxy. No single perspective reveals the whole truth. Only by combining observations across the full spectrum can astronomers see Andromeda in its entirety, from the tranquility of its outer disk to the intense energy near its core. Gazing upon it is like gazing upon the entire spectrum of cosmic life, from birth to death, all woven into a single celestial masterpiece spanning over 200,000 light-years. Precisely because of its proximity and typicality, Andromeda is one of the most thoroughly studied galaxies in the universe. Orbiting observatories have devoted countless hours to observing it. The Hubble Space Telescope has captured panoramic mosaics covering its entire vast structure. The Chandra X-ray Observatory has dissected its energetic core, and the James Webb Space Telescope scrutinizes its dusty outer regions with unprecedented detail. As a nearby laboratory, Andromeda helps scientists understand the physics of galaxies that apply across the universe. Because it is close and similar to the Milky Way, it makes possible the study of fine-scale processes that are impossible to discern in more distant galaxies. Every wavelength observed, every image captured, deepens our collective understanding of how galaxies live, age, and interact. Andromeda is no longer just a distant blur in the night sky. It has become a cornerstone of modern astronomy, a benchmark against which we measure our understanding of the cosmos. Looking back historically, the debate over Andromeda's true nature was once fiercely contested. Before the 20th century, no one knew exactly what it was. Through early telescopes, it looked like a fuzzy patch of mist called the Andromeda Nebula. Many astronomers firmly believed it lay within the Milky Way, a veiled, nearby star cluster. Others suspected it might be something far grander, perhaps an island universe beyond our own galaxy. This debate became one of the most passionate intellectual clashes in astronomy. Lacking precise distance-measuring tools, the truth remained hidden. Andromeda was both familiar and mysterious, visible to the naked eye, yet its true scale incomprehensible. They reflected humanity's growing curiosity about the universe, a deep-seated desire to know whether our home was unique and singular, or part of something far more magnificent. This uncertainty persisted until a single photograph emerged. One famous photograph finally settled the debate once and for all. In the early 20th century, astronomers began attempting long-exposure photography of the night sky. Among them, a photograph of Andromeda taken by Edwin Hubble using the Hooker telescope at Mount Wilson revealed extraordinary details. Embedded in the glowing spiral were faint, flickering points of light, Cepheid variable stars. By measuring their pulsation periods and apparent brightness, Hubble calculated their distance. The result shocked the world. These stars were millions of light-years beyond the edge of the Milky Way. The Andromeda Nebula was not a nearby gas cloud, but a complete galaxy teeming with its own stars. This single photograph permanently altered astronomy, transforming a mystery into a revelation, vastly expanding humanity's view of the true scale of the universe, and showing that our Milky Way is merely one of countless galaxies scattered throughout the vast cosmic structure. Edwin Hubble's work conclusively proved that Andromeda lies millions of light-years beyond the edge of our own galaxy. Using Cepheid variables as a measuring stick, he calculated Andromeda's distance to be over 2 million light-years. At the time, this was an almost unimaginable distance. This discovery shattered the long-held belief that the Milky Way was the entirety of the universe. Andromeda became the first confirmed galaxy outside our own, a window into the vastness of the cosmos. Hubble's precise measurements marked the birth of modern extragalactic astronomy. His work not only revealed Andromeda's true identity but also hinted at a grander truth. Space is filled with galaxies of all shapes and sizes, extending in all directions. This breakthrough forever changed humanity's perception of its place in the cosmos. For the first time, we realized we are part of a vast, expanding universe filled with countless other worlds glowing in the dark. That discovery permanently reshaped our understanding of the universe. When Hubble announced his findings in the 1920s, the scientific community was stunned. Previously, the prevailing view was that the Milky Way constituted the whole of creation. Recognizing Andromeda as another separate galaxy instantly expanded the known scale of the universe by an almost inconceivable factor. Overnight, the universe went from being a single island of stars to a vast ocean filled with countless islands. This realization redefined humanity's position in existence, changing our perception of scale, time, and possibility. It also paved the way for the even more revolutionary discovery that the universe itself is expanding. Thus, Andromeda became a symbol of perspective. It reminds us that even the most familiar corner of the sky may hide miracles beyond imagination, patiently waiting for human curiosity to sharpen enough to see them. It marked the great moment when we realized the Milky Way is not alone. Before Hubble's work, people looked up at the stars believing every visible light belonged to our own galaxy. The revelation that Andromeda was another galaxy changed everything. It meant the Milky Way was just an ordinary member of a much broader cosmic community. The universe suddenly ceased to be a single stellar city and became an infinite archipelago, with galaxies as its islands. This realization shifted astronomy from the study of our local environment to the exploration of the universe itself. It inspired generations of scientists and dreamers to look outward, beyond the boundaries of our own spiral arms. Whenever we see Andromeda rising in the autumn night sky, we remember that turning point when the boundaries of the known world dissolved and the universe opened up before us, inviting us on an endless journey of exploration. The Andromeda galaxy also helped reveal that the universe is vast and expanding. After confirming Andromeda was an external galaxy, Edwin Hubble continued observing other, more distant galaxies. He noticed that light from most galaxies was shifted toward the red end of the spectrum, indicating they were moving away from us. This observation led to one of the most profound conclusions in science. The universe itself is expanding. However, Andromeda is a rare exception, showing a blue shift that indicates it is approaching us. Its retrograde motion makes it even more important, proving that galaxies are not static points in space but dynamic participants in the grand motion of the cosmos. By studying Andromeda, astronomers can calibrate measurements of distance and speed, linking observation to theory. Today, Andromeda is both a neighbor and a key clue, a silent witness to the discovery that space-time is not fixed, but filled with motion and growth. The stars within Andromeda even became the ruler we use to measure the universe. The Cepheid variables Hubble discovered there laid the cornerstone of modern cosmology. These stars pulsate with a predictable rhythm. Their pulsation period has a strict correlation with their intrinsic brightness. By measuring the period, we determine the star's true luminosity, and by comparing that to how faint it appears from Earth, we can calculate its distance with surprising accuracy. This method forms the first critical rung on the cosmic distance ladder. Today, every measurement we make of galaxies, clusters, and the expansion rate of the universe traces its roots back to these stars. The light from Andromeda's Cepheids not only revealed its own remoteness but provided astronomers with the fundamental tool for mapping the scale of the infinite cosmos. The stars of our nearest neighbor became humanity's original yardstick for measuring the boundless universe, and their steady pulse continues to guide our exploration of the deep sky. The Cepheid variables within Andromeda were crucial for that pioneering measurement. Each one acts as a tiny, flickering beacon millions of light-years away. As the star expands and contracts periodically, its brightness waxes and wanes in a steady rhythm. By recording this pulsation rhythm, astronomers can read the star's true luminosity. Comparing this intrinsic luminosity to the faint light reaching Earth reveals the distance unequivocally. This method was the key to unlocking cosmic scale. Discovering these stars in Andromeda were so distant conclusively proved our galaxy is just one of billions. Today, refined by modern telescopes, the same technique is still used to measure galaxies far beyond Andromeda. These stars continue to beat their silent rhythm in cosmic time. The light reaching Earth serves as a steady message from the past, telling us not only where they are, but also measuring the long road human understanding has traveled since we first learned to decipher them. The light of Cepheid variables ultimately confirmed that Andromeda lies millions of light-years away. When Edwin Hubble measured the brightness of Andromeda's Cepheids, he found they were far dimmer than similar stars within the Milky Way. The only explanation was a staggering distance, a chasm spanning millions of light-years. That faint light began its journey to us long before humans walked the Earth, traversing the silent void between galaxies. Each pulsation of every Cepheid precisely encoded information about its true luminosity and distance. When Hubble compared the two, the result was irrefutable. Andromeda was not a local nebula, but a vast stellar realm existing beyond the borders of our own galaxy. This realization completely reshaped the human cosmic view, revealing that the universe extends far further than anyone had ever dreamed. And light itself became the ultimate messenger bridging the enormous gaps of space and time between worlds. That discovery made the universe appear unimaginably vast in our eyes. Before Hubble's measurements, the astronomy community widely believed the Milky Way encompassed all existence. When his calculations showed Andromeda was millions of light-years away, the scale of the known universe exploded. The Milky Way was no longer the sum of creation, but just one drifting galaxy among countless others. The scale of existence leaped from thousands of light-years to billions. This discovery changed not only science but profoundly altered the human perspective. We realized we inhabit a tiny world orbiting an ordinary star, which itself is just a speck within a single galaxy in an infinite universe. The revelation brought by Andromeda became a collective awakening. The universe was no longer a single structure, but an infinite landscape, vast and full of possibilities, where every faint smudge in the sky could be another galaxy, a home to countless stars and unimaginable worlds. Unlike most galaxies that are receding from us due to cosmic expansion, Andromeda is on a path heading inward. Precise spectral analysis of its light shows a slight shift toward the blue end, meaning it is approaching. The speed is astonishing, over 300 kilometers per second. Though it sounds incredibly fast, given the immense distance between the two galaxies, this collision will still take billions of years to occur. Andromeda's motion is driven by the mutual gravity of our two giant systems, gently but surely attracting each other through space. This approach is no accident. It is an inevitable consequence of gravity. It is part of the slow choreography governing the movements of galaxies within our local group. As the distance closes, their halos have already begun to overlap, mingling invisible gases and dark matter. The faint blue shift in Andromeda's starlight is the first subtle clue we have received that our destiny and its destiny are fated to intertwine on a galactic scale. Gravity, the oldest force in the universe, will eventually pull the two galaxies together. Over billions of years, the mutual gravity between the Milky Way and Andromeda will act like a slow but steady cosmic tide, pulling them closer despite the overall expansion of the universe. About 4 billion years from now, the two galaxies will begin their first close encounter, as their stars and gas clouds interact in a grand cosmic dance. Gravity will stretch their spiral arms into huge arcs of light, merging them into new patterns. Such events are not anomalies but a natural part of galactic evolution. Collisions like this have shaped the universe for billions of years, creating larger, more complex structures from smaller galaxies. The meeting of Andromeda and the Milky Way will not be a disaster, but a transformation, a graceful, slow-motion convergence that reshapes both into a brand new whole, shining persistently in the depths of the future cosmos. When they finally interweave and collide, direct impacts between individual stars will be rare. Despite the Milky Way and Andromeda each containing hundreds of billions of stars, the average distance between stars is so vast that the probability of any two stars directly hitting each other is nearly zero. Instead, the collision is fundamentally gravitational. The orbits of stars will bend and change within the combined gravitational field of the two galaxies. Some stars may be flung into long tidal tails, extending thousands of light years, while others will settle into new paths orbiting the common center of mass. However, the diffuse gas clouds within the galaxies will physically collide and compress, triggering violent bursts of star formation that will light up the future sky with newborn brilliance. Therefore, this event is not destruction, but reorganization. To a distant observer, it will look like two glowing spirals slowly embracing and merging into a single radiant entity, continuing to shine peacefully in the profound darkness. At that time, the orbits of the stars will simply be altered and reshaped. When Andromeda finally meets the Milky Way, gravity will become the cosmic sculptor carving a brand new celestial landscape. Stars that once orbited in near-circular paths will begin to trace complex ring or parabolic trajectories within the merged gravitational field. Some may be flung into vast arcs extending to the edges of the new system, while others might spiral inward to form a denser, brighter core. Over time, the two distinct spiral patterns will lose their symmetry, blending and transitioning into a single, slightly elongated structure. After the chaos of the first closed passage, the entire system will gradually tend toward a new dynamic equilibrium. From inside the future galaxy, the night sky will be completely transformed, filled with rivers and bands of light, quietly recounting the memory of two galaxies becoming one. If humanity or our descendants still exist billions of years from now, they will be privileged to witness an unprecedented cosmic spectacle. As Andromeda approaches, its appearance in the night sky will transform from a fuzzy patch into a growing, brightening disk, eventually expanding into a glowing, sprawling plain. At the climax of the merger, the sky will be dominated by glowing streams of stars stretching across the heavens, like countless rivers of fire flowing slowly through space. Viewed from Earth's surface, this sight will be surreal and overwhelmingly magnificent, an ultimate celestial show unfolding over millions of generations. Although the process is too slow to perceive in real time, its cosmic beauty will be unparalleled. Familiar constellations will vanish, and stars will rearrange into entirely new patterns. The future night sky will forever shine with evidence that galaxies, like life, are born, grow, and merge, leaving behind stunning traces of their union upon the firmament. As the two galaxies draw near, their mutual gravity will act like two invisible hands, twisting and stretching each other's spiral arms, dragging out massive amounts of stars and gas to form giant, glowing arcs. These elongated structures are called tidal streams, operating on the same principle as the moon's gravity causing ocean tides on Earth, but scaled up by billions of times. Each stream may contain billions of stars, stretched incredibly thin across intergalactic space. Some of these streams will eventually fall back into the merging core, while others may drift away forever, becoming faint light lost in the void. Astronomers have already observed similar streams around other colliding galaxies, giving us a preview of our own galaxy's future. These glowing cosmic bridges will be visible for billions of years, subtly testifying to the invisible gravitational bond that once drew the two spirals together and reshaped them into a single, radiant whole. After a long process of close encounters, tidal distortions, and spiral entanglements, The Milky Way and Andromeda will eventually merge into a stable new structure. Billions of years from now, their orderly spiral forms will vanish completely, replaced by a shape closer to a sphere, an elliptical galaxy. This newborn giant elliptical galaxy will be extraordinarily massive, containing all the stars, gas, and dark matter from both original galaxies. Astronomers have already observed many such giant ellipticals in the universe, and they are likely the products of ancient galactic mergers. The central black holes of both galaxies will also eventually spiral inward and merge, releasing gravitational waves that will shake space-time. Although it will take over 10 billion years for all the details to settle, the outcome will be serene, a massive, glowing sphere of stars shining quietly in the darkness of the cosmos. Some astronomers have already given this future galaxy a poetic name, blending the names of its parents, Milkomeda. The collision and merger of Andromeda and the Milky Way is not a single event, but a slow evolution spanning billions of years. When the galaxies first meet, they will pass through each other, continue moving outward under gravity, and then be pulled back for a second, and then a third, close passage. Each crossing will further twist their shapes, creating ring structures and streams that slowly settle and mix into the new stable structure. The merging process will be so prolonged that several generations of stars will be born, evolve, and die within its duration. Eventually, all chaotic motion will subside, replaced by the smooth symmetry of a giant elliptical galaxy. This timescale surpasses ordinary imagination, but on the scale of cosmic rhythms measured in billions of years, such events are commonplace. Time itself becomes the greatest sculptor, slowly molding two ancient spirals into an eternal monument of starlight and silence, spanning the deep. Although the future galactic merger will drastically reshape the macrostructure of the Milky Way and Andromeda, the space between individual star systems is so vast that our solar system will almost certainly survive the event unscathed. The Sun and its planets will continue their orbital motions, merely shifting to a new location within the newly formed galactic structure. It might be flung farther from the new galactic center or drift among unfamiliar stars, but the probability of the entire system remaining intact through the gravitational perturbations is extremely high. Over time, the night sky seen from Earth will change beyond recognition. New star clusters and streams will dominate, while the familiar Milky Band of the Milky Way will dissolve as its structure disperses. However, the Sun will still shine, the Earth will still orbit, and the sky will still be full of light. What seems like a violent cosmic collision from afar will glide past our little corner of the universe almost gently, leaving our solar system warm and vibrant. An intriguing question arises. If intelligent civilizations exist somewhere within the Andromeda galaxy, they may have already known of our existence. From their vantage point, they see the Milky Way as it was 2.5 million years ago, because light from the Earth and Sun takes that long to arrive. If their technology is advanced enough, they might even detect the faint spectral signatures of oxygen, methane, or other biomarkers in our atmosphere, just as we now search for biosignatures on exoplanets. But to them, humanity has not yet evolved. They see a primordial Earth bathed in starlight. Likewise, when we observe Andromeda, we see its distant past, not its present. Any civilization there is also looking back at an earlier version of us, just as we look back at them. The two galaxies have already engaged in a cross-temporal communication via light, the eternal messenger, though it is a communication destined to be fraught with agonizing delays. The image of the Milky Way in their telescopes is frozen in the distant past. If observers in Andromeda possess powerful telescopes, the image of our galaxy they see is not our home as it is now, but as it appeared millions of years ago. The finite speed of light means every observation is a look back through time. They would see the Milky Way before humanity existed, perhaps even before the first mammals appeared. From their perspective, our Sun might appear younger, and the spiral arms of our galaxy might look slightly different. This time delay works both ways. Our observations of Andromeda are equally ancient. Therefore, the space between galaxies is also the space between moments. It is a living archive of the past written in light. When we gaze at Andromeda's glow, we are not merely crossing spatial distance, but staring directly at history itself, illuminated by stars from eras long gone. If civilizations within both galaxies attempted to establish a dialogue, it would require superhuman patience. Any signal sent from Andromeda to us, even traveling at light speed, would take over 2.5 million years to arrive. Our reply would take another 2.5 million years to return. By the time a conversation could reach its second round, the civilization that initiated contact might have already changed or perished. The sheer scale of the universe renders real-time interstellar communication impractical. Yet, the idea itself is profoundly meaningful. It highlights the unimaginable vastness of the cosmos and the solitude of every world within it. Every intentionally sent message becomes a time capsule tossed into the dark abyss, a whisper that might, someday, be heard by others living in a completely different era in a distant place. In that vast silence, the universe remains eternally patient, forever listening. Based on probability, there are undoubtedly an astonishing number of planets in the Andromeda galaxy. Among its countless stellar systems, many planets must orbit within the so-called habitable zone, at the right distance from their star to potentially host liquid water. Although we cannot see them directly yet, statistical models strongly suggest that millions of Earth-like worlds may be scattered throughout its spiral arms, orbiting stable, sun-like stars. Some of these planets may have atmospheres and climates suitable for life. Others might be ice-covered worlds hiding global oceans beneath their crusts, or moons warmed internally by tidal forces. Future generations of telescopes may be able to detect the faint spectra of these distant worlds, revealing signs of oxygen, methane, or other potential indicators of life. The idea that Andromeda might harbor entire ecosystems, or even civilizations, sets the human imagination free. It reminds us that the universe's diversity and capacity for creating wonders may far exceed anything we have discovered so far, even exceeding our wildest dreams. Of course, not all potential life-bearing worlds orbit stars like the Sun. The diversity of stars in Andromeda ensures an equal diversity of planetary environments. Some planets may orbit massive blue giants, bathed in intense ultraviolet radiation. Others may cling to tiny red dwarfs, trapped in eternal twilight with one side forever facing their star. Still others may exist in binary systems, having two suns, casting double shadows in their skies. The immense variety of Andromeda's stars inevitably leads to an equally immense variety of worlds. Each system likely tells a unique story of chemistry, atmosphere, and light, offering nearly limitless possibilities for life and exploration wherever the galaxy's light reaches. Moreover, Andromeda may contain even more rogue planets than stars. These planets were flung out of their parent stellar systems during gravitational turmoil and now drift freely in the cold darkness between stars, homeless and solitary. The surfaces of these worlds might be permanently frozen, their skies forever dark. However, some may retain a trace of warmth from internal radioactive decay or residual geothermal heat, potentially harboring subsurface oceans of liquid water beneath icy crusts, hidden refuges for microbial life. Astronomers estimate that in a typical galaxy, the number of such rogue planets may exceed the number of stars themselves. This means Andromeda could harbor trillions of these invisible, lonely worlds. They are the true wanderers of the cosmos, each undertaking a silent, endless journey across the vast emptiness between suns, reminding us that even in the deepest dark, the universe is filled with quiet possibilities waiting to be discovered. Across Andromeda's vast expanse exist nearly all types of stars known to humanity. This galaxy is a complete laboratory for studying stellar evolution, from bright blue supergiants and bloated red giants to dense white dwarfs and rapidly spinning neutron stars. It also hosts a multitude of sun-like stars and a dominant population of dim, long-lived red dwarfs. This mixture allows astronomers to observe every stage of stellar life within a single galaxy, from its birth in glowing nebulae to its final resting place as a cooling ember. Stellar diversity also directly shapes the galaxy's overall color. Young regions shine blue, while old regions glow red. Each type of star contributes to the galaxy's metabolic cycle, together creating a living mosaic of light, representing almost every possible form of stellar existence in the universe. Encircling Andromeda's glowing disk are hundreds of ancient, globular clusters. These are dense, spherical collections of stars, each containing hundreds of thousands to millions of suns, packed tightly into a space only tens of light years across. These stars are among the oldest residents of the universe, formed when the cosmos was still young. Their light is soft and golden, their motion stable and serene. Studying them allows astronomers to look back to the early epochs of galactic history, revealing how Andromeda and its companions first assembled. These globular clusters form a sparse, crown-like halo around the galaxy, glowing faintly at its edges. Some of them may be the remnant cores of dwarf galaxies devoured by Andromeda long ago. They are the ancient guardians of the galaxy, running their silent orbits as they have for 10 billion years, preserving the memory of when the first stars began to shine. Among Andromeda's many globular clusters, several are veritable giants. The most famous, known as Mayol 2 or G1, is not only the largest globular cluster in Andromeda but one of the largest known in the entire local group. It contains millions of stars, tightly bound by gravity, with a total mass exceeding that of many dwarf galaxies. G1 is so bright that it appears as a faint point of light next to Andromeda even in mid-sized amateur telescopes. Astronomers believe it is likely the heart left behind from a dwarf galaxy swallowed by Andromeda in the distant past, its outer stars stripped away while its dense core survived intact. Clusters like G1 serve as fossils of cosmic history, preserving clues about Andromeda's growth and the merger events that shaped it. They demonstrate that even within the seemingly placid exterior of a star cluster lies a story written in light, a tale of creation, collision, and enduring survival. Not all globular clusters behave properly. Some of the clusters orbiting Andromeda exhibit strange dynamical properties that are difficult to explain with simple gravitational theory. Their stars move in unexpected patterns, rotating at abnormal speeds or having overall shapes that are slightly elongated and distorted, as if pulled by some invisible force. Astronomers speculate that these odd motions might hint at the influence of dark matter, or they could be relics of ancient merger events in Andromeda's history. The peculiar dynamics within these clusters are like fingerprints of ancient cosmic events. Perhaps two clusters merged in the past, or maybe the shockwave of a close passage disturbed them. Studying these anomalous clusters helps scientists uncover Andromeda's more secret evolutionary history and the subtle, mysterious forces that continue to operate within its vast halo. Though invisible to the naked eye, Andromeda possesses a grand magnetic field permeating its spiral arms and halo. Radio wave observations show that these magnetic field lines trace elegant patterns, following the movement of gas and stars, stretching for thousands of light years. This magnetic field is generated by the rotation of the galactic disk combined with the motion of ionized gas, acting like a giant cosmic dynamo. It plays a vital role in the galaxy's life, guiding the flow of high-energy cosmic rays, shaping interstellar clouds, and possibly even influencing the rate of star formation. Though intangible, Andromeda's magnetic field is one of its most beautiful hidden features, an invisible network of energy connecting its stars and nebulae in a subtle, ever-shifting balance. High-energy particles known as cosmic rays constantly bombard the galaxy. Inside Andromeda, the motion of these particles is not entirely random. They are guided and confined by the galactic magnetic field. The magnetic field forces them to travel along spiral paths, preventing them from escaping easily. When cosmic rays interact with the gas and dust in the galaxy, They produce faint radio and gamma-ray emissions that can be detected by equipment on Earth. By observing this radiation, scientists can indirectly trace the structure and strength of Andromeda's magnetic field. Understanding how cosmic rays behave within a galaxy also reveals how energy cycles on cosmic scales, transferring momentum and heat through the interstellar medium. It is a complex, ongoing process, a quiet dance between microscopic particles and the magnetic structures that guide them. In this way, Andromeda demonstrates that even the most minute forces can participate in shaping the fundamental rhythm of an entire galaxy. When astronomers observe Andromeda with gamma-ray telescopes, they find that the galaxy emits a faint but distinct glow of high-energy gamma radiation. These extremely energetic photons do not come from ordinary stars, and the source regions do not seem to correspond to any obvious visible objects. One exciting explanation is that this radiation might originate from the decay or mutual annihilation of dark matter particles, though this remains unproven speculation. A more conventional possibility is that they are produced by cosmic rays accelerated to extreme energies within Andromeda's magnetic field. Whatever the cause, these gamma signals reveal that this seemingly tranquil galaxy is far from dead. Deep within its halo, massive energy processes may be underway, releasing photons powerful enough to pierce 2.5 million light-years and enter our telescopes. Every detection provides new clues for understanding the invisible forces at play in the universe. Dark matter is invisible and intangible, but according to some theories, when dark matter particles collide, they may reveal their presence through the emission of faint gamma-ray radiation. The mysterious gamma-ray glow detected in Andromeda's halo has given some scientists hope that they are witnessing this process. If true, the Andromeda galaxy would become a natural laboratory for studying one of the universe's greatest mysteries. Detecting radiation originating from dark matter would provide very direct evidence for its existence and help determine the nature of its particles. Although the signal is currently weak and interpretations are not unique, the potential implications are profound. It suggests that beneath Andromeda's serene appearance lies a deeper story, one not written in stars or light, but in the invisible physical laws that govern the structure of the universe itself. In the X-ray view, Andromeda displays a face completely different from the visible one, full of violent energy. Scattered across its disk and halo are countless bright X-ray sources. Many of these are powered by the remnants of dead stars, neutron stars, white dwarfs, and especially black holes, as they accrete matter from companion stars, heating gas to millions of degrees. Interspersed among these compact objects are diffuse clouds of extremely hot, thin gas, likely the remnants of ancient supernova explosions. X-ray light allows us to peer into the galaxy's ongoing life cycle, showing how the energy released by dying stars affects the interstellar medium and triggers new star formation. Through these observations, astronomers can see the violence and renewal coexisting within Andromeda, the endless cycle of transformation that defines its evolution across cosmic time. Among the many X-ray sources, some particularly bright points stand out. These are believed to be black hole binary systems, consisting of a stellar mass black hole and a normal companion star. As the black hole's gravity pulls matter from the companion, the material forms a rapidly spinning, superheated accretion disk before plunging into the event horizon, emitting intense X-rays. Such systems are among the most efficient engines in the universe, their brightness easily detectable across intergalactic distances. Observing them allows scientists to study how black holes feed and grow, and how energy is released from the most extreme environments known. Each such system is a miniature drama of creation and destruction, a cosmic stage where gravity, motion, and light converge, challenging the limits of human understanding with its intensity. The Andromeda galaxy does not create stars at a constant rate. Over its history of more than 10 billion years, it has experienced several violent starburst periods. During these times, gas in certain regions of the galaxy was compressed so severely that the rate of star formation spiked dramatically, birthing massive numbers of stars in a short span. These bursts left lasting imprints on the galaxy's structure, filling its arms with bright clusters of young blue stars. Astronomers believe these starbursts were often triggered by gravitational interactions with neighboring galaxies, which disturbed the gas distribution and stirred up waves of creation. Between these bursts, Andromeda enters quieter phases where star formation slows, allowing gas to cool and regroup. This rhythmic cycle of activity and rest reflects the galaxy's natural breathing, a slow heartbeat pulsing through cosmic time. Many of the stars we see shining in its arms today may carry the memory of one of these ancient eruptions. Galactic mergers are common triggers for star formation bursts. Throughout Andromeda's long history, it may have experienced multiple mergers or close encounters with other galaxies. When a smaller galaxy passed through or near Andromeda, its gravity acted like a stirring spoon, disturbing Andromeda's gas disk, compressing gas clouds, and triggering massive waves of star birth. Evidence of these ancient mergers is preserved in the peculiar distribution of stars, the warped shape of the galactic disk, and the faint stellar streams extending beyond the visible edge. Thus, past mergers are not just records of destruction, but moments of renewal. They injected Andromeda with new matter and energy, helping it grow into the magnificent structure we see today. Many stars blazing in Andromeda's spiral arms may owe their birth to such ancient cosmic encounters. In the vast halo beyond Andromeda's bright disk, astronomers have found faint scars left by collisions long ago. Slender arcs of stars and diffuse streams mark the final paths of smaller galaxies torn apart and eventually consumed by Andromeda's gravity. These ghostly traces are incredibly difficult to observe, but with the most sensitive telescopes, astronomers can track them like detectives following fingerprints. Each mark tells a story of a merger that occurred billions of years ago, when the universe itself was relatively young. By studying their shapes and motions, scientists can reconstruct the chronology of Andromeda's growth, much like archaeologists piecing together a dinosaur from fossils, revealing how it evolved through countless such interactions. The halo, though seemingly empty, is full of memory. Every star drifting within it may be part of an ancient echo, a silent witness to the collisions and fusions that shaped this majestic galaxy. These slender stellar streams are essentially fossil records of these ancient events. In the outer regions of Andromeda's main body, these linear structures stretching hundreds of thousands of light-years are the debris of smaller galaxies slowly shredded by gravity. Their scattered stars now form glowing trails, precisely tracing the orbits they followed before being devoured. Astronomers call them tidal stellar streams, and they are like living fossils preserving events from billions of years ago. By analyzing their positions, motions, and chemical compositions, scientists can piece together the story of Andromeda's formation. Just as paleontologists reconstruct dinosaurs from fossils, astronomers reconstruct the galaxy's merger history from these streams. Within their faint light lies the memory of creation, written in the quiet periphery of a galaxy still coalescing from the dust of past mergers. For years, astronomers thought the visible edge of Andromeda marked the end of its domain. But deeper, more sensitive observations reveal that its stellar halo extends much farther than previously imagined. This halo, composed of sparse stars, globular clusters, and stellar streams, may extend nearly halfway to the distance of the Milky Way. The discovery of this massive halo has changed our definition of a galaxy's true size. Andromeda is not just the bright spiral we see through telescopes. It is a colossal gravitational structure occupying a significant portion of the local group space. Its halo is a mixture of the new and the old, containing both the oldest stars in the universe and the fragments of recent merger events. It is a vast, dissolving frontier connecting Andromeda to intergalactic space. Within this enormous halo, the ages of stars vary enormously. Astronomers have identified some stars that are over 10 billion years old, among the oldest in the universe. Others appear much younger, likely immigrants stripped from smaller galaxies only recently merged with Andromeda. This age mixing indicates that the halo is not a static museum, but a constantly evolving environment. New stars are added through ongoing gravitational interactions, while ancient stars drift slowly over time. Thus, the halo is both an archive preserving relics of the distant past and an active construction site, continuously receiving the products of more recent cosmic events. It is by studying this complex environment that scientists have gradually understood how galaxies accumulate their mass and structure like rolling snowballs. Every star in the halo adds a new clue to Andromeda's ongoing growth story. In the outermost regions, far from Andromeda's bright core, its halo becomes so thin that it blends seamlessly with the vast, near-empty expanse of intergalactic space. There is no sharp boundary, no wall marking where one ends and the other begins. Instead, the density of stars and gas decreases smoothly until it merges into the faint background of the space between galaxies. This borderless transition profoundly indicates that galaxies are not completely isolated islands in the cosmic ocean, but nodes in a continuous cosmic web, their spheres of influence overlapping. The outer halo is the region where Andromeda's gravitational influence finally yields to the gentle tug of the cosmos as a whole. In that territory, free-roaming stars and clusters wander, no longer belonging definitively to any center. Observing this peripheral region gives astronomers a rare glimpse into the connection between a galaxy and the larger environment it inhabits. It is the quiet edge of a system that never truly ends, but merely dissolves softly into infinity. Many of the stars scattered throughout Andromeda's halo are tens of billions of years older than our Sun. Some may be over 13 billion years old, formed shortly after the dawn of the universe. These ancient suns have burned for an unimaginably long time, their light remaining constant while countless civilizations may have risen and fallen on distant worlds. Studying them allows astronomers to look back at the physical and chemical conditions that existed near the beginning of time. Their chemical composition shows extremely low levels of heavy elements, indicating they formed before the universe was polluted by the first generations of supernovae. Hidden within their faint light are the records of the earliest nucleosynthesis processes that shaped all later stars. These ancient lights continue to shine quietly throughout Andromeda's vast territory, linking the galaxy's current grandeur to the deep origins of the universe itself. Yet, even in a galaxy filled with ancient stars, creation never ceases. In Andromeda's spiral arms and diffuse gas clouds, new suns are being born at this very moment. Inside glowing nebulae, gravity pulls cold hydrogen gas into dense clumps that eventually collapse under their own weight, igniting nuclear fusion. These young stars illuminate their surroundings with their brilliant energy, causing nearby gas clouds to glow pink and red. Some are massive, short-lived stars. Others resemble our Sun, capable of burning stably for over 10 billion years. The sharp contrast between newborn stars and ancient neighbors tells a story of continuity, a cycle that has never been interrupted since the galaxy first formed. Every new star contains the recycled products of countless previous generations of stellar matter, proving that even in a universe over 10 billion years old, the creative process continues in the soft glow of Andromeda's nebulae. The elements composing Andromeda's stars tell a long story of gradual enrichment. The oldest stars consist almost entirely of hydrogen and helium, the primordial ingredients left over from the Big Bang. However, younger stars show traces of heavier elements like carbon, oxygen, iron, and even gold. These heavy elements were not present from the start. They were forged in the internal furnaces of previous generations of massive stars and violently scattered into interstellar space when those stars died as supernovae. Over time, this cycle of creation and destruction gradually polluted or enriched Andromeda's gas clouds, making each successive generation of stars chemically more complex than the last. By analyzing the spectra of these stars, astronomers can reconstruct this chemical evolution spanning 10 billion years, tracing how the galaxy transformed from a simple vortex of primordial gas into a fertile environment capable of forming rocky planets and potentially life. In this way, Andromeda's chemical makeup is both a timeline and proof of the endless cycle and renewal of matter in the universe. Each generation of stars breeds the next with heavier elements. When a massive star reaches the end of its life and explodes as a supernova, it scatters its enriched contents, newly synthesized heavy elements, into space. This ejected gas mixes with the surrounding interstellar medium, eventually forming new nebulae from which new stars are born. Thus, each new generation inherits more heavy elements than the last, slowly but surely changing the galaxy's overall chemical composition. In Andromeda, this process has been going on for over 10 billion years, gradually converting simple hydrogen into the diverse array of elements that make up the complex universe. The oxygen we breathe, the carbon in our bodies, the iron in our blood, all originated in such stellar furnaces. Therefore, the glittering light of Andromeda is not just the radiance of distant suns, but evidence of this ongoing cycle of creation. The galaxy itself is like a giant cosmic alchemist, forever transforming the simple into the complex, forging the building blocks of life in the endless rhythm of its stars' births and deaths. When stars in Andromeda form from gas enriched by previous generations, the planets orbiting them inherit these same elements. Thus, planetary systems scattered throughout Andromeda may possess rocky surfaces, metallic cores, and complex carbon-based molecules, much like Earth. Some may have oceans or atmospheres filled with water vapor, carbon dioxide, or methane. Others may have icy rings or volcanically active moons. The presence of these heavy elements suggests that the conditions necessary for complex chemistry, and even life, may be widespread throughout the galaxy. Although we cannot yet see these distant worlds directly, the light from their parent stars carries the spectral signatures of the elements that compose them. In this way, Andromeda is like a mirror to our own Milky Way, a galaxy similarly sprinkled with the raw ingredients for life across billions of stars. Each such system is a potential miracle, quietly waiting to be discovered across the vast gulf of space. To the naked eye, Andromeda's light appears steady and eternal. However, precise astronomical measurements reveal that its overall brightness actually fluctuates very subtly over time. These changes stem from the occasional eruption of supernovae, the periodic pulsations of variable stars, and the movement of dust and gas clouds obscuring or scattering starlight. Certain regions temporarily brighten due to the birth of young star clusters, while others dim slightly due to the death of massive stars. Even the large-scale motion of interstellar dust can cause minor fluctuations in its overall apparent brightness. Although these changes are minuscule and hard to detect, they reveal a key fact: galaxies are not static sculptures, but living systems, slowly breathing through cycles of creation and decay. Long-term monitoring of these tiny variations allows astronomers to track Andromeda's ongoing evolution. Its light is both constant and ever-changing, a cosmic heartbeat perceptible only across the ages, a gentle reminder that even the most distant, magnificent things are in eternal motion. These slow fluctuations in brightness reveal the heartbeat of the star formation cycle. The rhythm of Andromeda's survival and breathing operates on a timescale far grander than the human one. Across its massive spiral disk, light rises and falls in cycles spanning millions of years. Astronomers studying its long-term brightness changes have detected this slow, repeating pulse, precisely tracking the pace of galactic creation. Gas clouds collapse to form newborn star clusters and light peaks. Then, as the matter is exhausted or blown away by stellar winds, the region gradually dims. The galaxy brightens, dims, and brightens again, following a steady beat measurable only through centuries of patient observation. It is as if the galaxy has its own heartbeat, not beating in seconds, but in epochs. Witnessing these subtle changes is like sensing a cosmic breath, inhaling gas, exhaling starlight, creating and resting in a balance as eternal as gravity itself. Astronomers can even detect the rotation of the Andromeda galaxy itself. This colossal entity is spinning in space at a slow, elegant pace, imperceptible to any eye. Scientists discovered this by analyzing its spectrum. The light from one side of the galaxy is slightly blue-shifted as it moves toward us, while the light from the other side is red-shifted as it moves away. This Doppler effect indicates that the entire galaxy is rotating like a giant wheel, with its billions of stars participating in this majestic motion around a common center. Every point of light we see is a fragment of this grand movement. Completing one full rotation takes hundreds of millions of years, a span in which the Earth might experience multiple cycles of species rise and fall, yet the galaxy's rotational rhythm remains unshaken. By precisely measuring its rotation speed, scientists can weigh the total mass of the galaxy, thereby revealing the presence of dark matter, whose mass far exceeds that of all visible matter and holds the stars captive. It takes Andromeda hundreds of millions of years to complete a single rotation. In that almost inconceivably long stretch of time, the Sun could orbit the center of the Milky Way several times, and the Earth might witness multiple mass extinctions and explosions of life. Yet Andromeda's rotation is unhurried. Every star, every nebula, moves steadily along its gravity-dictated orbit. Centripetal force provided by gravity and centrifugal force from stellar motion achieve a delicate balance, allowing the spiral structure to persist for billions of years. Imagining this slow rotation is like glimpsing the deeper rhythm of cosmic time, where seconds, years, and centuries lose all meaning, leaving only the eternal dialogue between gravity and motion. The galaxy moves without haste, yet with absolute certainty, carrying within its ancient spin the complete record of billions of suns being born, shining, and returning to stardust. Although its billions of stars are all moving individually, the spiral pattern of Andromeda has remained remarkably stable for billions of years. This seems paradoxical, but it is not. Those elegant spiral arms are not made of fixed stars. They are density waves propagating through the galactic disk, like sound waves traveling through air, but on a gargantuan scale. When the wave front of the density wave passes through a gas-rich region, it compresses the gas, triggering star formation, which instantly lights up the arm with young, blue star clusters. As the wave moves forward, the previously bright region gradually fades, while the area ahead is lit up by the next wave of star birth. Thus, the pattern of the spiral arms remains stable, but the stars composing them are constantly changing. Gravity, conservation of angular momentum, and the collective behavior of interstellar gas together maintain this exquisite structure over time. In a universe where change is the norm, this is a dynamic, enduring harmony. Seeing Andromeda's spiral is witnessing order born from motion, a perfect balance so profound it seems to possess life. These arms are not merely features of light, but echoes of the eternal forces shaping cosmic structure in space. Adjacent to Andromeda's bright disk is a smaller, elliptical smudge of light, its companion galaxy, Messier 32. Compact and dense compared to the Master's grand spiral arms, M32 appears like a smooth sphere of tightly packed ancient stars. It is far more than just a target for our telescopes. It is a cosmic autobiography suspended high above our heads. From the ancient bewilderment regarding that faint patch of light, to the astounding revelation of Hubble unveiling its galactic nature, to our precise mapping today of its collision course with the future, the story of Andromeda is, in essence, the story of humanity's ever-expanding cognitive horizons. It teaches us humility, that the Milky Way is not unique. It grants us perspective, that our worries and glories unfold on a tiny planet within a galaxy destined to merge with its neighbor. The next time you look up on an autumn night, trying to spot that faint glow with your naked eye, may you remember that you are gazing not just at a distant realm of a trillion suns, but into a giant mirror spanning time and space. Reflected within it are the first glimmers of light from the inflation of the universe, the life elements forged in stellar furnaces, the patient weaving of gravity over 10 billion years, and a quiet invitation from the distant future, a promise of fusion and new life. Tonight, let this light, which began its journey 2.5 million years ago, carry your thoughts and grant you profound tranquility within the infinite expanse of time and space. This is Science of Everything. We'll see you next time.